of our summer school. This morning's lecture will be given by Professor Patricia Palacios, who teaches philosophy of science and philosophy of physics at the University of Salzburg. Today, she will give us a lecture entitled On the Use of Universality Arguments in Black Hole Physics. I remind you that during the lecture, you can write in chat F if you have clarification questions. For other questions and discussion, we will wait at the end of the lecture, and you can book by writing a Q in the chat. So don't write your questions in the chat. So that said, I give the floor to Professor Palacios.
So I have to accommodate these screens with your faces here. Okay. Thank you for the introduction. I'm very happy to be part of this wonderful event, wonderful summer school. So what I will present today is largely based on a paper that I wrote with Shangri and Karim Thibault, which is now forthcoming in the British Journal for the Philosophy of Science. But I will try to go this time a little bit beyond this paper, and I will discuss the consequences of our analysis in this paper for the use of analog experiments in black hole physics. So I will be talking about analog experiments in black hole physics quite a bit. So now let's start. As you all know, in 1974 and 1975, in the two papers, Stephen Hawking famously predicted that black holes weren't so black after all. So he said that there was something that could escape a black hole, and that's what we call thermal radiation, or nowadays Hawking radiation. I understand that tomorrow you will talk in quite a bit of detail about Hawking radiation with Eric Curiel, so I will just give you a very short summary of Hawking radiation in case you are not familiar with it. So the idea of Hawking radiation, as you know, is that when a star collapses to a black hole, the space-time becomes non-trivial. And it is possible that the ground state of a quantum field evolves into a state with excitations, which in other words means that we can find a flux of outgoing particles at future null infinity, even if there is no flux of ingoing particles from past null infinity. We talked about this Penrose diagram with Eric yesterday, so I assume that you are familiar with it. And Hawking predicted furthermore that this flux of outgoing particles will be associated with a certain temperature that is written by this expression. So temperature is proportional to the surface gravity, which is a measure of acceleration. And near the future null infinity at later times, which means near the time-like infinity, we will observe that this Hawking radiation has exactly this temperature, and that the Hawking radiation is also independent on the initial state of the ground state, and is independent on the details of the collapse. So in other words, Hawking predicted that Hawking radiation is robust upon the initial state of the ground state of the quantum field, and it is independent or insensitive to the details of the collapse. So now this robustness of the Hawking radiation upon the details of the collapse depends on three conditions. First of all, we need that, first of all, we observe that at a distant future, there will be an exponential redshift of the free-falling modes. And this implies then that these modes were created by ultra-high frequency modes. So we will be talking about this later. We also need some regularity conditions that require that the modes observed near the distant future or near time like infinity are in the ground state near the horizon. and we need an event horizon that creates a causal barrier between the ingoing modes and the observers confined to the exterior regions of the black hole. So this is basically Hawking radiation in a nutshell. As I said, you will talk about this in detail tomorrow with Eric Courier. And to quote Eric again, so it turns out that physicists, so almost the entire community, as Eric said, 98% of the physicists are very confident about the existence of Hawking radiation. And more generally are very confident about black hole thermodynamics. So this is a strong belief in physics, but we as philosophers put this a little bit into question and ask, for example, is there any empirical evidence for Hawking radiation, for this prediction? And if not, is there at least strong theoretical evidence for this prediction? Or in other words, are there strong theoretical arguments that make us trust in Hawking radiation? And I will show today that in order to support some empirical evidence for Hawking radiation, and in order to support the existence of theoretical evidence, we need what we call universality arguments. So what are universality arguments? The notion of universality is very widespread in physics. So we have here about universality in many senses. But in condensed matter physics, the notion of universality took a very precise meaning associated with the occurrence of phase transitions, in particular continuous phase transitions. So Michael Barry, for example, said that universality is the slightly pretentious way in which physicists denote identical behavior in different systems. So in other words, the notion of universality is the idea that certain behavior is going to be instantiated in different systems. Or yet, in other words, is the idea that certain systems behave quantitatively and qualitatively exactly in the same way. So this idea, as I said, this very precise meaning of universality comes from condensed matter physics, when it was observed that different systems like fluids and magnets behave exactly in the same way close to a critical phase transition. Here is a diagram, for example, that shows how 8 different fluids behave quantitatively in the same way when in the transition from liquid to gas. This picture is taken from a paper by Guggenheim from 1945. So when we talk about universality arguments in the context of black hole physics, we have something like this in mind. So we don't talk about universality in the sense that a phenomenon is everywhere or that a law is valid everywhere, but we talk about universality in the sense that the same behavior is instantiated in different systems. And moreover, when we examine the use of universality arguments in black hole physics, we can see that universality arguments are not only supporting or proving the universality of certain phenomena, but also proving the robustness of certain phenomena. And in this sense, it's very important to distinguish between robustness and universality. Universality, as I said before, is the idea that certain behavior is instantiated in different systems. So we can understand this universality as type insensitivity. So that is the idea that some behavior is insensitive to changes in the macroscopic details that characterize the type of systems that we are considering. For example, a behavior can be the same in stationary and non-stationary black holes, or it can be the same in astrophysical and eternal black holes. So that's the idea of universality.
Excuse me, Patricia, yes? Eric Curel has a question for you.
Yes.
So, Patricia, I just want to make sure that I understand the way that you're using type and token here, because you're saying that different ultraviolet physics is a token level variation. So I would have thought the token meant like individual system, like, you know, this cup of tea right here, not the type would be tea in general or fluid in general, but each cup of tea, presumably the token, the type cup of tea, they all have the same ultraviolet physics. So that's not how you're using type token here, I take it.
That's not, sorry, the last part.
So that's not how you're using type token here, I take it. Can you just tell me how you're using type token?
Okay, perfect. Yes, so universality, so different types means that different classes of systems, let's say.
Okay.
So the fluid, a particular fluid can be a type of fluid, and a magnet would be a different type of system, right?
Okay.
So when we say that a behavior is insensitive with respect to different types, means that we can change the type, so we can change the system, and we still have the same behavior.
Okay.
So in other words, that means that the same behavior is instantiated in systems as different as fluids and magnets, for example. So the behavior remains invariant when we change the type, when we change fluids for magnets.
Okay, and how are you using token?
Token is a little bit more. It's used in the standard sense of philosophy, but here we said that the robustness of a certain, so the robustness is the insensitivity of a certain in the behavior in a certain type of system, like a fluid, for example, under different token variations.
Mm-hmm. But this is where I'm confused, because to me, the phrase different ultraviolet physics seems to connote that you're talking about a class of systems that all share these same ultraviolet physics, not an individual system that has its own ultraviolet physics.
Now I'm thinking about the insensitivity of some behavior of a particular type of system, or in a particular type of system, to variation of different microscopic details that can be understood as variation.
Oh, okay. I'm sorry.
That's the idea.
I'm sorry. I think I'm just being incredibly stupid. I think I now understand what you're saying.
Yes.
So you're saying that, so good. The ultraviolet physics is part of the type, and it's insensitive to the token level variation. Got it. Sorry, I was just being a complete bonehead.
Don't worry. I think that clarification helped everyone. So universality again can be understood as type insensitivity. So it's the insensitivity of some behavior to changes of the macroscopic details that characterize type of systems, or in simple words, that is the idea that the same behavior is instantiated in different types of systems, whereas robustness is the insensitivity of some behavior in a particular type of system. So here we are not we are not comparing different types. We are focusing on a particular type of system to variation of microscopic details that we call token level variation. For example, different modifications in the ultraviolet regime. So what we realize is that universality argument, or so-called universality arguments that are used in black hole physics, are actually robustness universality arguments. So these are arguments that prove that a certain behavior of theory, yeah.
Sorry. There is another question from Pavan.
Yes.
I just wanted to clarify again. So if two systems have very different kind of ultraviolet Lagrangians, and they exhibit the same behavior, that would be universality and not robustness, right?
Sorry, can you say the last part? I think the audio is not perfect, but you can.
So if two systems have very different Lagrangians, microscopic Lagrangians, and their long-range behavior is same, you would classify that as universality and not robustness, right?
Perfect. Yes, you got the idea. Okay. That's exactly the point. Okay. Yes, exactly. Exactly.
Right,
exactly.
Thanks.
So two systems can have a different Lagrangian or a different Hamiltonian at the fine grain level, but if at the coarse grain level they have the same Lagrangian or the same coarse grain Hamiltonian, they will be an instantiation of universal behavior. That's exactly right. So universal behavior then, it's when the same behavior is instantiated in different types, to put it in simple words, and robustness is when we have a certain behavior in a type of system that is invariant under microscopic perturbation. So in the case of robustness, we focus on the behavior of a specific type. In the case of universality, we compare the behavior between different types. And what I said is that we realized that universality arguments in black hole physics are universality robustness arguments. So these are arguments that prove that a behavior or a theory. I will not distinguish here between behavioral theory because I think it can be valid in both. So a behavioral theory is both robust and universal. That's what I think that a better name for the so-called universality arguments are robustness universality arguments. So that's very important to have in mind because this entire lecture is going to be about universality arguments. So it's very important to be clear about what we mean by universality arguments. And as I said, universality arguments have been used widely and now more and more in the context of Hawking radiation in order to justify the certain experimental evidence of Hawking radiation and in order to justify also the strength of theoretical arguments given in the context of Hawking radiation. So, but the question is, how can we assess the strength of these arguments? So how good are universality arguments and to what extent can universality arguments help us justify certain empirical evidence for Hawking radiation and to what extent universality arguments can also help us justify theoretical evidence for Hawking radiation. So that's the main question of today. And I will follow the following strategy, which is the strategy that we follow in our paper. So in order to evaluate the strength of universality arguments given in the context of Hawking radiation, we compare them with very successful universality arguments, which were offered in condensed matter physics by Wilson, which are called the Wilsonian renormalization group methods arguments. So we take the Wilsonian universality arguments or the Wilsonian framework as an exemplar of universality arguments. And using this as an exemplar or as a template, we try to establish a general framework that will allow us to evaluate universality arguments also in the context of black hole physics. And this framework will be based on 6 qualities or 6 categories that I will explain later in this lecture. So these are robustness, physical plausibility, degree of universality, comprehensiveness, empirical support, and integration. Integration is going to be the most important quantity that in this framework. And what we do then is to apply this framework to the universality arguments for Hawking radiation. And just to anticipate the conclusion, it's not as good as one would expect. So after comparing Wilsonian universality arguments with the universality arguments used in the context of black holes, we conclude that universality arguments for Hawking radiation fail to measure up to their Wilsonian counterparts, being integration the most important problem. Exactly what consequences have this for the possibility of having some empirical evidence for Hawking radiation is something that I will discuss. And I will also discuss the consequences of this for the so-called theoretical evidence for Hawking radiation. So this is the plan for the rest of the lecture. First of all, I would like to explain a little bit more clearly why we need, to some extent, universality arguments in the context of Hawking radiation. So yesterday with Daniel, we discussed different theoretical problems that arise in black hole physics when we try to combine thermodynamics with a quantum field theory and quantum gravity. Also, Eric talked about that. So one of the problems is the information loss paradox, which is one of the main topics of this summer school. But another problem that wasn't mentioned yesterday, and that is very important, and is going to be the problem that I will focus on today, is the Transplanckian problem. So as I said, one of the conditions for the robustness of Hawking radiation and the insensitivity of Hawking radiation with respect to the physics of the collapse is that at the distant future, we will observe an exponential redshift in the outgoing particles. That means, conversely, that the outgoing particles originated from modes with extremely high frequency radiation, in frequencies that go beyond the Planckian scale. Why is this problematic? So this is called the Transplanckian problem. Why is this problematic? It's because in the Transplanckian scale, so in scales that go beyond the Planckian regime, the semi-classical framework, that is quantum field theory in quark spacetime, that is presupposed in Hawking derivation, breaks down. So Unruh framed this problem in a very dramatic way that I like. So he says, if one examines Hawking's original calculation, there are some severe problems with his derivation. While mathematically impeccable, they are nonsense physically. Frequencies which are needed to explain the radiation produced even 1 second after a solar mass black hole forms correspond to energies which are e to 10 to the 5 times the energy of the whole universe. So this is a very dramatic way of putting of framing the Trans-Planckian problem. So how can we deal with this problem? A possible way of dealing with this problem, and maybe the best way of dealing with this problem, is precisely showing that Hawking radiation is both robust and universal in the sense that I described before. Why do we need this? Because we need to show that even if an implication of the conditions for robustness of Hawking radiation implies or tells us that the modes were created by high energy frequencies, we could try to deal with this problem if we show that high energy or high frequency effects don't matter for the Hawking radiation, for the existence of Hawking radiation. So what we need to show is that Hawking radiation is insensitive with respect to different possible ultraviolet physics, and therefore insensitive with respect to possible quantum gravity effects. So in other words, we need to show that Hawking radiation is robust. But not only that, we also need to show that Hawking radiation is universal. So we need to show that exactly the same Hawking radiation that is instantiated in one type, in a specific type of black hole, is also instantiated in other types of black holes. So the same Hawking radiation that is robust upon different possible ultraviolet physics is instantiated in different types of black holes, being them astrophysical black holes or eternal black holes, and even analog black holes and real black holes. So taking how I defined universality arguments before, what we need, or what we can do in order to solve the Trans-Planckian problem, is to use universality arguments, which would mean that we need to show that Hawking radiation is both robust upon possible ultraviolet physics and universal, so that is the same Hawking radiation that is robust upon ultraviolet physics, the one that is instantiated in different types of systems, astrophysical, eternal, rotational, and stationary. So it seems that in order to solve at least that theoretical problem, in order to defend that there is theoretical support or theoretical evidence for Hawking radiation, we need universality arguments. And something similar happens with the possibility of having experimental evidence or for Hawking radiation. So Eric said in his lecture yesterday that there was no empirical evidence for Hawking radiation, that empirical confirmation was impossible in the context of Hawking radiation and in general in black hole thermodynamics. And many physicists would agree with him. Actually, it seems to be virtually impossible to do an experiment directly in a black hole. In order to test, for example, Hawking radiation, we would need to test radiation in a black hole that is very big and is very close to the solar system. So in a way, it is true that one cannot perform direct experiments in black holes. But some physicists would think or would disagree with Eric in the sense that they believe that even if we cannot have direct experimentation in black holes, it is possible to have experimental support of black hole thermodynamics and even Hawking radiation by using analog experiments. And this has been a very important topic in physics, opened a new branch of physics that is called quantum analog gravity. And it has been also a very important topic of discussion in the philosophical literature. So this idea that we might be able to use analog systems in order to test empirically the predictions of black hole thermodynamics came from a paper, an insight from Unruh in 1981, where he suggested that we could find an analog of black hole evaporation by studying the behavior of sound waves in fluids. So he says, it is shown, for example, in the abstract of the paper is the following. He says, it is shown that the same arguments which lead to black hole evaporation also predict that a thermal spectrum of sound waves should be given out from the sonic horizon in transonic fluid flow. In this paper, he just suggested the analogy between sound waves in fluids and a black hole and real black holes. He didn't, so this is not the exposition of any experiment, but recently many experiments have been performed trying to make sense of Unruh's prediction. And he's quite confident here that the use of this analogy between sound waves and light waves could actually help us perform real experiments that might give us an experimental support for the predictions in black hole thermodynamics. So he says a physical system exists which has all the properties of a black hole as far as the quantum thermal radiation is concerned, but in which all of the basic physics is completely understood. In this system, so this is the analog system, one might even contemplate the experimental investigation of the thermal emission process. In many,
sorry again, Patricia, don't hate me. There is another question. There is another question for you.
Yes, could you explain the dimensional analysis argument in the previous slide? I just missed it. Or, oh no, the slide before, yeah, that slide. What was the gist of that?
Yeah, this is just part of the paper here, so I would have to go into a little bit more detail. Okay, maybe we can discuss it later.
Yes.
But I will say something more about the analogy, about the formal analogy between the analog system and the real system, if you don't mind. I think that will give you a clearer idea of what is behind this argument. Okay, great. So as I said, Unruh was quite confident that this analogy would also help us give some empirical support for the predictions in black hole thermodynamics. And this is, so here are more details, this is how the analogy works. So this is what philosophers would consider a formal analogy, or strictly speaking, a liberal formal analogy, because the equations are not exactly the same, but they seem to have exactly the same role in the different theories. So as I said, the analogy here is between real black holes and the behavior of light waves in real black holes with the behavior of sound waves in fluids. And it was predicted that if we assumed that the background fluid in the analog case exceeds the velocity of sound, which is denoted by c here as the velocity of light, then the propagation of sound can be understood as being governed by an acoustic metric of this form here, which is analogous to the Schwarzschild metric near the horizon of a black hole. As I said, this is a liberal formal analogy because the equations are not exactly the same, but they seem to occupy the same role in both theories. And in the analog case, there will be actually an acoustic horizon, which will divide the fluid in a region, in a subsonic region, in which the velocity of the sound will be smaller than the velocity of the fluid, in a supersonic region in which the velocity of the sound will be, in which the velocity of the fluid will exceed the velocity of the sound. And he also predicted that this, in the analog case, the sound waves will be associated with a thermal spectrum analogous to the Hawking radiation, which with this temperature, which is also analogous to the temperature associated to Hawking radiation. As I said, again, the temperatures are not identical, but they seem to be analogous in an obvious way, as you can see here. So this idea that we can find a Hawking effect by studying the behavior of sound waves in fluids give rise to a very important enterprise in which physicists started, where physicists started elaborating experiments, real experiments, performing real experiments in black hole, in analog systems, with the hope of getting some confirmation of the thermodynamic, of the predictions of black hole thermodynamics. So the reason why this was taken so seriously by physicists was that in the case of in the hydrodynamic case, we know the physics very well. So it was believed that these analog systems could help us studying the origin of the outgoing particles, which is something that we could not do directly by studying the black hole. And it could help us testing the robustness of Hawking radiation. So we could try, for example, to solve the Trans-Planckian problem by seeing whether in these analog systems Hawking radiation was insensitive with respect to microscopic perturbations. And these analog systems were also supposed to teach us something about quantum entanglement, because in principle, we could observe quantum entanglement between the Hawking phonons and their partners in the analog system, which is something that we cannot observe directly in the real black hole. So physicists start studying this with this insight, start studying the possibility of Hawking effects in Bose-Einstein condensates, especially in order to test the entanglement. And in 2000, for example, Garay et al. Derived a Bose-Einstein condensate Hawking effect using the hydrodynamic approximation. And in 2009, Recati et al. Showed that Bose-Einstein condensate Hawking radiation was robust upon changes at wavelengths that are larger than the healing length, which is the analogous to the Planck scale in the real black hole. So the idea was that since they could show that Bose-Einstein condensate Hawking radiation was robust upon changes at wavelengths larger than the healing length, one could extrapolate this robustness to the case of real black holes, trying to solve in this sense, among other issues, the Trans-Planckian problem. And very remarkable progress on this project has been done by the Israel Institute of Technology, or the Technion, especially due to Steinhauer and collaborators. For example, in 2010, Steinhauer and collaborator created a Bose-Einstein condensate analog black hole. So they create the actual experiment, the actual system. And in 2016, so very recently, Steinhauer said that he observed, so he was able to observe quantum Hawking radiation and its entanglement in this analog black hole. And for him, this means actually that there is empirical evidence and empirical support for black hole thermodynamics, and in particular for the existence of Hawking radiation. So in a conference that he gave in 2017, he says that black hole thermodynamics has been verified experimentally in his analog experiments. But we are philosophers, so we question this kind of claims. And what we are interested in is in asking, for example, whether it is true that analog experiments can provide empirical confirmation of Hawking radiation in the target system. After all, we are not performing experiments directly on black holes, but we are performing experiments on a source system, on an analog system. So are these analog systems capable of giving us empirical support, or even stronger empirical confirmation for the predictions of black hole thermodynamics like Hawking radiation? And if so, which kind of confirmation is the confirmation that analog experiments provide? So this has started a debate in philosophy. Some philosophers, in particular Karim Thibault and collaborators, which is also my co-author in the paper that I'm discussing today, he's very optimistic with respect to the use of analog experiments, and he says that analog experiments can provide empirical confirmation of Hawking radiation in the real black hole if we have good universality arguments. And he thinks that we have good universality arguments. So in a way, the Hawking radiation has been confirmed thanks to the experiments in the analog systems. And a little bit more, so in 2019, he makes a stronger claim, and he says that the type of confirmation that analog experiments provide is of the same kind as traditional experiments that are performed directly in the target system. So he says, if universality arguments are accepted, they would function as external validation of the Steinhauer's experiments, which means that we can extrapolate the results of Steinhauer's experiments to real black holes. So he says they can be used to confirm general statements regarding astrophysical black holes. Crowther and co-authors, including Chris Wutrecht, are a little bit more pessimistic in this debate, and they said that these arguments are incapable to support the empirical confirmation provided by analog systems, especially because these arguments all assumed that the semi-classical framework is independent of the trans-Planckian physics, which is something that we need to test. So in order for universality arguments to work, they said we need to assume that the semi-classical framework is robust. But this is one of the things that we wanted to test in the first place. So it seems that these arguments are begging the question. So these are so far the main two possibilities or the main two positions in the debate. I will now try to defend some intermediate position between these two. Just to let you know that the notion of universality or the word universality in the context of black holes is not used only by philosophers, but it has also been used by physicists. For example, Unruh and Schutzhold in 2005 titled the paper on the universality of the Hawking effect. And even if they don't define universality explicitly as we do, they implicitly use it in a similar way. So in this paper, they try to find the necessary and sufficient conditions for having Hawking radiation in different systems. So this, what I have said today, open different philosophical or motivate different philosophical questions that I will address in the rest of the lecture. First of all, is how strong are these universality arguments, or how strong are the universality arguments that have been given in the context of black hole physics? The second question is, are these arguments strong enough to justify the use of analog experiments? And the third question is, are they strong enough to solve the trans-Planckian problem? So these are very big questions. I will try just to give you insights on how to answer each of them. So as I said, in order to evaluate the strength of universality arguments given in the context of Hawking radiation, we compare these universality arguments with our paradigm example of universality arguments, which are the Wilsonian universality arguments. So now I will talk a little bit about the Wilsonian universality arguments, and I will tell you why these arguments are so good and why these arguments would be very helpful to solve the kind of problems that we need to solve in black hole physics. So as I said before, the idea of universality took a very precise meaning in condensed matter physics. So this is the idea that in condensed matter physics, this is the idea that at the critical point, certain systems, different types of systems, as different as magnets and fluids behave not only qualitatively, but quantitatively in the same way. This can be seen very clearly by the fact that near the critical point, different systems follow power law behavior, which is associated with a critical exponent here. So in the case of continuous phase transitions, one sees that the critical exponent is identical or very, very close for a diversity of systems. And the diversity of systems that have the same critical exponent associated to it are said to be in the same universality class. So this, of course, the fact that all these systems have the same value of the critical exponent assure us that the behavior is going to be not only qualitatively, but also quantitatively the same close to the critical phase transition. And one of the most important achievements in the theory of phase transition was the explanation of the universality observed among different systems by Wilson. So Kenneth Wilson won the Nobel Prize in 1982, actually, because he gave an explanation of universality of condensed matter physics, which was then extrapolated also to other fields of physics. So the explanation of universality was called renormalization group methods. So he developed this on the basis of the work done by Kadanoff before. And I will not go into a lot of details on what renormalization group methods are, but it's very important to give you a very general idea of these methods, which actually provide an explanation of universality. So the idea of renormalization group methods is that we should define a transformation that is called a renormalization group transformation that coarse grains the system. And we should do that successively until we arrive at a fixed point. And we will observe that different systems with the same renormalization group transformation flow towards the same fixed point. And this is the explanation, very roughly, the explanation of universality. So in a little bit more detail in this framework, what one does by using a specific transformation is that one integrates out short-range wavelength modes up to a finite cutoff in momentum space. And then one examines how the coupling constant change by changing the value of this cutoff successively until we arrive at a fixed point. And the coupling constant here can be classified between in three groups. So relevant coupling constants, irrelevant coupling constants, and marginal coupling constants. The relevant coupling constant will grow when we apply this transformation. And this helps us define the surface in this framework. The irrelevant coupling constant will disappear when we use the renormalization group transformation. In the marginal coupling constant, will arrive at a fixed value at the infrared regime. So this is important because the disappearance of the irrelevant coupling constant allow us to conclude that the behavior at the critical point is robust upon different details in the microphysics. And at the same time, the disappearance of the irrelevant coupling constants allow us to justify why we can use why the same behavior can be instantiated in systems that are very different at the fine-grained level. So it seems in a way that this framework, the renormalization group framework, allow us to demonstrate that the behavior close to a critical phase transition is robust, so it doesn't depend on irrelevant couplings. And by doing that, it allows us to explain why different systems behave exactly in the same way close to a critical point. And this is because the details that distinguish the different systems at the fine-grained level are not important at the critical point. So these arguments serve us to justify then the robustness of the theory of critical phenomena and the robustness of critical phenomena itself and the universality of critical phenomena too. So we studied this framework, and as I said, we took it as a template to build a more general framework that would allow us to evaluate other types of universality arguments. And we conclude that this framework can be characterized by 6 main properties that are robustness, universality, physical plausibility, comprehensiveness, empirical support, and integration. And this renormalization group method scored very high in all these properties. So now I will explain these properties in a little bit more detail because they are going to be important then for the evaluation of universality arguments in black hole physics. So the robustness, as I said before, can be defined as insensitivity upon single type token variation, or insensitivity of some behavior in a particular type of system upon microphysics. Robustness in the case of Wilsonian arguments is very high because one can show that most of the coupling constants are irrelevant. Actually, the critical behaviors seem to depend only on the spatial dimension and the symmetries of the original parameters. The universality here is also very high because one can demonstrate that different systems, including models like the 3D Ising model and ferromagnets and liquid gas, are in the same universality class, so that these systems behave exactly in the same way, close to the critical point. And physical plausibility in this case is also very high, because by using these arguments, we can actually justify the use of models like the 3D Ising model for studying the behavior of real systems, like real ferromagnets and real liquid gas transitions. Comprehensiveness is the size of the set of observables over which robustness and universality arguments can be applied. Comprehensiveness in the case of Wilsonian arguments is also very high because the arguments apply to almost all relevant observables. And the empirical support in this case is also very high because one can show that one can calculate the values of the critical exponents associated to different universality classes by linearizing around fixed points in this framework. So the empirical support here is also very good. And most importantly, integration here is very high. So what is integration? This is going to be a key property in our analysis. So integration is the idea that the theoretical basis behind the invariance found in the universality arguments and the robustness argument is mutually consistent. In this case, the integration is maximal in the case of Wilsonian arguments, because the basis, the theoretical basis for robustness and universality is actually exactly the same. It is by showing that a certain behavior is robust upon a microscopic perturbations that we can justify it and we can explain universality, which is the idea that different systems will behave the same at the critical point. So integration here is maximal and it's very high. So now, why are these arguments important? So as I said, Kenneth Wilson won the Nobel Prize for elaborating the renormalization group approach. But these arguments are also very important in order to give, in order to validate the theory of critical phenomena, for example, as an effective theory. That would mean that the arguments are very important to validate the theory of critical phenomena as a theory that can tell us everything what we need to know at a certain scale. Why is this? Because the renormalization group methods give us a very good argument to conclude that the theory of critical phenomena can be applied safely to different types of systems, at least to the systems that are in the same universality class. And it tells us that the theory is robust in the sense that it doesn't depend on microscopic details. So what I believe is that renormalization group methods in this sense can help us justifying or interpreting the theory of critical phenomena as an effective theory. And with Wilsonian arguments can also help us justify the use of models and experiments to understand critical phenomena. For example, because one can show that the 3D Ising model is in the same universality class as real transition from, or as the transition from liquid to gas in real fluids, and the transition of paramagnetism to ferromagnetism in certain real materials. One can then justify the use of the 3D Ising model in order to understand the behavior of real fluids and the behavior of real materials that undergo a transition from paramagnetism to ferromagnetism. Another example of a universality class is planar spin models, which are shown to be in the same universality class as superfluid helium and superconducting metals. So the fact that we have universality arguments here help us justify the use of these models, of planar spin models, to analyze the behavior of real superfluid helium. And moreover, the use of renormalization group methods here help us justify the use of analog experiments among the members of the universality class. For example, experiments on helium films have been used in physics to study the behavior of some other magnetic systems. And they can trust on the results, on the extrapolation of the results of the experiments on helium films to other members of the universality class, because there are renormalization group methods that support the idea that that the behavior that is instantiated in these different systems is exactly the same. So it seems that universality arguments, or Wilsonian universality arguments, help us to be more confident about the use of analog experiments among the members of the universality class. So the idea would be to have something like this in the case of black holes, in order to both validate the theoretical evidence that exists in favor of Hawking radiation, and in order to validate the possibility of using analog systems to test the predictions of black hole thermodynamics. So what we did then was to compare the Wilsonian universality arguments, which are very strong, with the universality arguments that were offered in the context of black hole thermodynamics. But as I anticipated before, we conclude that the universality arguments offered in black hole physics are not as good as one would expect. So now let me tell you why. So we analyzed 3 types of universality arguments, which we think are the most important ones in the literature on black hole thermodynamics. So the first type of argument was an argument based on the equivalence principle. So if these arguments use the equivalence principle of Einstein between gravitation and acceleration to identify what is called Unruh radiation with Hawking radiation. So in a little bit more detail, they identify the Hawking radiation detected by some stationary observer outside the event horizon with the Unruh radiation detected by a Rindler observer with the same acceleration in a Minkowski space. And then, because there are Wilsonian style arguments, in the case of Unruh radiation, they thought that we could extrapolate the robustness of Unruh radiation to the case of Hawking radiation. So this is more or less the idea of the arguments based on the equivalence principle. We analyzed this framework by having by comparing them with the Wilsonian arguments, and we conclude that in comparison to Wilsonian arguments, they score very badly in almost all properties that characterize Wilsonian arguments. So they score very good in universality, but the high degree of universality come at the price of sacrificing robustness, even if the motivation of this argument was to imply some robustness in the Wilsonian, in the Hawking radiation. So now I will tell you in more detail why they score low in almost all properties with respect to Wilsonian arguments. So the robustness here in these arguments is very low. First of all, because the thermal properties of the Unruh spectrum are invariant under a large class of Lorentz invariant modification, but they are not invariant, or they are not insensitive to non-Lorentz invariant cutoff and to a variety of quantum gravity effects. So Unruh radiation is invariant to large class of Lorentz invariant modification, but it's not invariant to many possible quantum gravity effects. And what we want to test in the case of, or what we want to show in the case of Hawking radiation, is that Hawking radiation is robust upon different quantum gravity effects. So we don't achieve robustness in the sense that we would, or to the degree that we would desire in this case. And furthermore, it seems that this equivalence principle depends very sensitively on the fact that the observers need to be very close to the horizon. As soon as we move a little bit farther away to the horizon, the equivalence principle doesn't work anymore. So it seems that one cannot make inferences regarding the behavior of a late time detector far away from the horizon, since the parameters of the Hawking spectrum depend functionally on global properties of the space-time. But the degree of universality in this case is very high, so one can apply these arguments to Rindler and Schwarzschild spacetimes, and it can be extended to various other types of black holes, like astrophysical black holes. But the physical plausibility is very low. So as I said before, running the same argument for any observer other than one infinitesimally close to the horizon leads to the wrong answer. So it seems that the argument of the equivalence principle depends very sensitively on the fact that the observers should be very close, infinitesimally close to the horizon, and it doesn't work if we move from that. Therefore, there are no possibilities of de-idealizing this argument, and the physical plausibility is very low. Comprehensiveness is very low, so they focus only on one observable, that is the temperature, and the empirical support is very low or non-existent. It's absolutely lacking here. And integration, which, as I said, is the idea that the arguments of the theoretical arguments for universality and robustness are mutually consistent, is also very low, because it seems that we have universality here at the price of sacrificing robustness. So universality and robustness are in tension with each other, are not mutually consistent. And the second class of arguments are the arguments from the horizon symmetries. So here they use representations of Virasoro algebra. So they represent the Klein-Gordon modes as, so they write the Klein-Gordon modes as representations of the Virasoro algebra. And in 1+1 dimension, they show that there is a broken conformational symmetry of the horizon geometry. In this broken symmetry implies the generation of Goldstone bosons, which by applying the Cardy formula and giving many complicated steps, one can show that these Goldstone bosons have Bekenstein-Hawking entropy associated to it. So since these Goldstone bosons have Bekenstein-Hawking entropy associated to it, they interpret Goldstone bosons as Hawking fluxes. And now, since Goldstone bosons are robust, so they are invariant under a wide range of possible microphysics, they assume that Hawking radiation is also robust, because as I said, they identify Goldstone bosons with Hawking fluxes. So the main claim here is that thermal Goldstone bosons are interpreted as Hawking fluxes, and that because Goldstone bosons are robust, we should extrapolate that robustness to Hawking fluxes and Hawking radiation. So this is the result. So we compare again these arguments with the Wilsonian arguments, and this is the result of the comparison. So they seem to do a little bit better than the arguments based on the equivalence principle, but they still do pretty badly in comparison with Wilsonian arguments. In particular, they score very high in robustness, but they score very low in universality. And again, it seems that the robustness, so the increase in the degree of robustness, comes at the price of lowering the degree of universality. But comprehensiveness here, in contrast to the previous case, is very high. So now let us see these properties in detail, or these qualities in detail. So why the robustness is high in this case? Because one can show that any UV modification that preserves horizon symmetries will produce the same spectrum of Goldstone bosons. So this is very good news for the robustness. So it seems that Goldstone bosons are robust about any possible UV or high frequency, high energy modification. But the universality here is very low. So it seems that robustness comes at the price of lowering universality. In particular, because at present, the Goldstone bosons have only been computed for a restricted class of horizons, where the horizon is highly symmetric and evaporation effects are ignored. So in other words, Goldstone bosons have been computed only under very ideal situations, and it's not clear that that they can be extrapolated or they can be found in more realistic scenarios. For example, it is not clear that they can be applied to real black holes with evaporation effects and with collapse processes. That means also that the physical plausibility in this case is very low. So it is not clear that physically realistic horizons, such as the event horizons of astrophysical black holes, can indeed be effectively described using Virasoro methods, since there is no proof that the reduction to 1+1 dimension can adequately encode the physics of the collapse. But comprehensiveness is very high, so all observables can be computed directly from symmetry considerations. Empirical support here again is inexistent, so it's lacking. And integration is very low because the high degree of robustness here sacrifices the possibility of universality. And the final class of arguments that I would like to discuss are the arguments for modified dispersion relations. So these arguments were suggested by Unruh and Schutzholt in 2005 in the same paper that I mentioned before, that is called The Universality of the Hawking Effect. And these are, to our view, the strongest arguments, the strongest universality arguments offered in the context of Hawking radiation. So here what they do is try to test the effect of quantum gravity perturbations by studying a modified dispersion relation of this form, in which this square here is the Schwarzschild D'Alembertian, and this P is the square momentum operator. And this F is a mass term, and this mass term satisfies 4 conditions that are crucial in this framework. That is analyticity, irrelevance in the infrared. That means that when the eigenvalue associated to a square momentum operator goes to 0, this mass term also goes to 0. Subluminar, that means that the modes travel slower than light. And there is a scaling limit, which means that when this eigenvalue goes to infinity, the general mass term takes a constant value in the UV. So as you can see here, these arguments are very analogous to the Wilsonian arguments. In fact, the general mass term can be interpreted as a running coupling in simple truncation of the scalar field theory. So when we compare these arguments with the Wilsonian arguments, we see that these arguments do much better than other universality arguments. But again, they score very high in universality, but very low in robustness. And the high degree of universality seems to come again at the price of lowering the degree of robustness. But they are better than others because the physical plausibility of these arguments is moderate, and it is contingent whether they have empirical support. In the paper, we said that the empirical support is moderate, but now I am slowly changing my mind, so I'm not so sure about this anymore. But it can be said that there is some empirical support, at least for these arguments. So now let us see this in detail. So why robustness is very low here, in particular because they focus or they think that they can test the quantum gravity effects only by analyzing the behavior of this mass term. And it is not clear at all that this mass term can serve us to evaluate all possible changes at the UV, or all possible changes at the high energy regime. Universality here is high, which is the main virtue of these arguments, because it is applicable actually. So these arguments are applicable to a huge range of physical systems. For example, various types of eternal and astrophysical black holes, stationary and rotational black holes, and also to a wide variety of analog black holes. Actually, the arguments of dispersion relations here are the arguments that are behind the use of analog experiments in black hole physics. And the physical plausibility is moderate because one incorporates physical features of astrophysical black holes. The only thing that we need is that there is no back reaction, but we can be more realistic, or apply these arguments to more realistic situations. And comprehensiveness, so this is the how many observables are considered in this framework. Comprehensiveness is here again very low because it only applies to the occupation number of the Hawking modes. And the empirical support, we can say it's moderate because all analog experiments have been built by the assumption of these arguments, the dispersion relation arguments. So we can say that the fact that we can use analog experiments can be taken as empirical support of this argument. Although, as I said before, I am now not so sure about this, because in order to say that analog experiments provide some confirmation of the target system, we need universality arguments. And here we are saying that we justify universality arguments on the basis of these analog experiments. So to some extent, this seems to be a little bit circular. But at least some philosophers and physicists have thought that these arguments have empirical support because it is the basis of analog experiments. We can discuss this more in the Q&A. In integration here, it's again very low because it seems that the high degree of universality of these arguments come at the price of focusing only on this mass term, which reduces the degree of robustness. So now I will go to the conclusions. So what I believe are the consequences of our analysis for the use of analog experiments in physics, in black hole physics in particular. So as I said, all the experiments that have been performed on black holes have used the argument of modified dispersion relations. So that is the third family of arguments that I was discussing. These arguments have a high degree of universality. So these arguments can be applicable to a huge number of physical systems, ranging from eternal and astrophysical black holes to analog black holes. But as I said, they have a big problem that they are not robust. So they are highly restrictive with respect to the class of possible modifications to the physics of black holes. And the degree of comprehensiveness is also very low, since they only focus on the occupation number of the Hawking modes. What I believe is that in order for analog experiments to be more conclusive, one would need to use integrated arguments. So not only universality arguments, but integrated arguments in which the theoretical framework for robustness and universality is mutually consistent. We haven't found integrated arguments in the context of black hole physics yet, which means we cannot be so confident about the results of our analog experiments and about the extrapolation of the results of analog experiments to the target system, which is the real black hole. So these are some bad news for the use of analog experiments, but it doesn't mean that we can never, also that we cannot have these arguments, that we cannot develop these arguments in the future. It just means that we have not developed these arguments, these integrated universality arguments yet. And now, what are the conclusions of our analysis for the resolution of the Trans-Planckian problem? As I said, so one way of solving or trying to solve the Trans-Planckian problem is to show that Hawking radiation is robust and universal, so that it doesn't depend in the end on quantum gravity effects or high energy effects, and that it is universal. That means that the same Hawking radiation that doesn't depend on quantum gravity effects is instantiated in different types of systems. In order to prove that, we would need to have integrated universality arguments, but at the moment, we don't have those arguments, which means that the Trans-Planckian problem is still unsolved. In fact, the available universality arguments for Hawking radiation failed, as I said, to measure up their Wilsonian counterparts, and in particular, they failed to be integrated. In fact, what we saw is that in the Hawking case, in contrast to the Wilsonian arguments, the universality arguments that do well on degree of robustness do poorly on degree of universality and physical plausibility, and the arguments that do well on degree of universality do poorly on degree of robustness. So this seems to be a very pessimistic conclusion, but one can might think that it will be possible maybe to combine these different systems, these different arguments, in order to have arguments or a sort of a consistent framework that is both, or that supports both robustness and universality of Hawking radiation. So a possibility, for example, would be try to combine the arguments of the horizon symmetries with the arguments for the modified dispersion relation. Yet the coherence of such combined approach, it hasn't been developed yet, so it's yet to be seen. And there are some open questions that I'm interested in investigating in the future, and that we can discuss here if you want, that we didn't address in that paper. One of the questions is whether we can have integrated universality arguments in cases in which the target system is inaccessible. So Crowther et al., including Chris Budrich, said that when the target system is inaccessible, we will not be able to have universality arguments that justify the use of analog experiments or the external validation of analog experiments. And what we conclude here in our analysis was that the universality arguments used in the context of black hole physics were not integrated. But an open question, I think, is whether this is necessarily so. So one possibility to answer this question would be try to study other systems that are inaccessible, that are different from black holes, and try to see whether one can have in those systems integrated universality arguments. So this is something that we have started thinking about by studying other system, non-thermal fixed points. Another question, more philosophical question, is what type of arguments are integrated universality arguments? So are these inductive arguments? Which type of inductive arguments? Are these deductive arguments? So if we think about the renormalization group methods, there is a sense in which these arguments seem to be deductive too, or are a combination of both. So this is also something that hasn't been answered yet. And the third question is, to what extent can integrated universality arguments conclusively justify the use of analog experiments in black hole thermodynamics and in other fields of inaccessible targets? So these are just some of the open questions that one might ask on the basis of what I have presented today. And that's all. Thank you.
Okay, thanks a lot for your lecture. I think that there is enough time for a short break of 10 minutes if you want.
Yes, we can take a break of 5 minutes.
5 or 10 minutes
Yes.
as you want. Okay, okay.
5 minutes would be fine.
Okay, see you in 5 minutes.
Okay.
Okay.
Okay, thank you.
Questions? If there are questions, please let me know by chat or by your hand. Okay, there is a question by Emilia, please.
Yes, hello. Thanks for the talk. It was really interesting. And I was just wondering about this, this method of doing an analog experiment when you can't access what you really want to do an experiment on. And you mentioned some good examples, if you can call it that, of with the critical behavior. But I was just wondering whether this is something that has been done in other cases, and in that case, have there been analyses similar to what you have done for the Hawking radiation?
So the question is whether so analog experiments have been performed in other systems, or whether we have compared universality arguments in the context of black holes with other type of universality arguments that are not the Wilsonian arguments.
Not necessarily whether it has been compared to the black hole, but just whether something like what you've done here has been done for other cases of analog experiments, if you know that.
Other cases of analog experiments independent on black hole physics. So
yeah, if you
okay,
if you just know whether this exists.
Yeah. So analog experiments exist everywhere in science, even in medicine, for example. When you try to get some information about humans performing experiments in mice, you are using mice as your source systems to learn about the target system that are humans. So basically, even if now in philosophy of physics, the attention has been put in the use of analog experiments in the context of black holes, analog experiments have always been there. And not only in physics, but beyond physics, like the example that I just gave you. Now, in the context of black holes, they have been using other types of systems too, but the most important analog systems now are Bose-Einstein condensates, the ones that I was mentioning. The most important results are also coming from there.
Okay, yeah, thank you.
Okay, we have another question from Grace Field.
Yeah, thank you so much for the talk. I just wanted to go back, I think, to the first question that you raised yourself about whether you think it's actually possible to find universality arguments that are integrated for inaccessible systems. I'm just wondering what you think about that question.
Yeah, thank you. Those are the open questions. I cannot give you a definite answer, but these are the kind of things that I'm interested in investigating next, actually, with Karim to go to. So we were looking at non-thermal fixed points in long-range interacting systems, like even magnetic systems that that have some gravity, where you cannot get rid of gravity so easily, so you have to consider long-range interactions. So we might be analyzing that in order to see whether you can have some kind of integrated arguments in those cases in which the system is somehow inaccessible. But we haven't done the analysis yet, so I cannot tell you some definite answer. But my intuition is that you can, and that will give us hope about the possibility of having integrated arguments in black hole physics too. So that's the idea, to consider now another system that is inaccessible, that is not necessarily a black hole. And if we see that there are integrated arguments, which we think they are in the case that we are looking at the moment, but we haven't done the careful analysis yet, then that will give us hope for the use of for the possibility of integrated arguments in black hole physics too. That's the idea.
There's a case in the paper by Karim Thébault and Pete Evans where they discuss stellar nucleosynthesis, I think, as an example of an inaccessible system that we nevertheless think we can genuinely learn about, even though we can't access it and manipulate it. But they think that we can learn about it because of uniformity principles that tell us that atoms in the sun should decay, the nuclear reactions should happen in the same way.
Yeah, it's not so clear if the background arguments are integrated though in that case.
Well, this is what I'm wondering. Would you say that that's an example of a universality argument?
I'm not sure, because the arguments behind them don't look anything like Wilsonian arguments. So I'm not so confident that they will rely on integrated arguments in the end. So that's why I'm more interested in studying other types of systems in which they analyze inaccessible system by using arguments that look much more like Wilsonian arguments. I think that might be a better place to start.
Yeah. Okay, interesting. Thank you.
Thank you.
The next question is from Vincenzo Fano.
Hi, Patricia. Many thanks for your wonderful presentation. Can we say to everyone your wonderful situation in general, or it is something too much private?
No, you can say.
All people must say that Patricia is expecting. This is a very, we are very, very, it is very beautiful that she has been available to give this conference, even if it is a very personal situation. So I thank especially Patricia for this great, great. Yeah, okay. Thank you very much, Patricia.
In the 7th month, actually. So you would be able to see me very big if I would stand.
Yes. Not easy to give conferences at the 7 months. Wonderful. Your presentation was very, very beautiful. Thank you very much. I was discussing with Enrico about a very general point. We understood that you are not discussing the epistemology of Hawking radiation in general, but only the fact that Hawking radiation is not universally robust enough to be experimentally tested. Is this the point, or you have also some doubt about the general deduction of Hawking radiation? Because in this case, the most important argument favoring Hawking radiation is not universality and robustness, but the fact that from very different general hypotheses about what happened at the Planckian scale, we arrive at the same plus or minus at the same conclusion. This is the point.
Yeah, thank you. So the motivation when we start working in this paper was actually focusing on the use of analog experiments. So that, but in the end, in the paper, we hardly talk about analog experiments. So the paper was most about the Hawking radiation in general. So I think we need, as I was saying at some point in the talk, I think we need universality arguments for both, for justifying the use of analog experiments in the context of black hole physics, but also for justifying not Hawking derivation. Hawking derivation is mathematically impeccable, so no one will doubt on it, but to justify the physical plausibility of Hawking radiation. So because as I said, in order to say that Hawking radiation is plausible, we need to say that, or at least is plausible and valid in the semi-classical regime, we need to say that Hawking radiation is robust upon possible quantum gravity effects. So it doesn't depend on quantum gravity in the end. In order to show that, we need universality arguments. You need arguments that show that there is that robustness that we need in order to say that the semi-classical framework is sufficiently autonomous and doesn't break down with the possibility of quantum gravity effects.
And what do you think about the fact that even if Hawking radiation is not sufficiently robust and not sufficiently universal, it could be deducted through different roles? Because if you speak with the theoretical physicist, the main argument favoring in his her head is the Hawking radiation is that it is possible to deduce it in different ways, very different ways. I think I listened many times this kind of argument. What do you think about this argument?
Can you repeat the last part? Sorry, I lost it.
Okay, when one speaks with a theoretical physicist and ask why you believe in Hawking radiation even if we have no experimental data, the main argument I listened many times is okay, because you can deduce the Hawking radiation from very different theoretical hypotheses. So the argument is not concerning universality and robustness, but something much more theoretical. What do you think about this kind of argument?
No, in a way that is an argument for robustness too. So you said that the calculations are robust, or the results are robust because you arrive at the same results by different methods. But what I would say is that's an argument of robustness that helps us to be more confident of Hawking radiation. But we need something more. We also need to say, in order, for example, to solve the Trans-Planckian problem, we also need to show that Hawking radiation is robust upon possibility of quantum gravity effects. So I think that's consistent with what I said, but I think we need more robustness in order to trust.
So you conduct this kind of argument to robustness. Okay.
Yes, that's also robust. Yes.
Thank you very much.
Yes, thank you.
Okay, Manus Visser has another question for you.
Well, let me first congratulate you on the pregnancy as well, and thanks for the talk. I also have children at home, so I know what the next phase you're going in. So my question is actually quite general about why you compare the universality in Hawking radiation to universality in fixed points. I'm a little worried that the universality in critical phenomena is super high, and that it's a bit unfair to compare universality in Hawking radiation, which is not a critical phenomena, to that kind of universality. Of course, the universality is very well defined using Wilsonian methods, but I think it's more reasonable to maybe just use some more general notion of universality and then discuss whether Hawking radiation is universal and robust with respect to those notions, which is a very valid question, of course, but comparing it to critical phenomena, I'm a bit hesitant that makes, yeah.
I think your question is also very valid. I'm glad you asked that question, because it's about the motivation of this project in the first place. I agree with you. So maybe the type of universality that we find in condensed matter physics is the highest type of universality that we can have. And as you say, we cannot demand of this black hole or analog black hole systems to have the same degree of universality, so to be governed by the same equation with the same analogous to critical exponent or the same values. Actually, we are not thinking about quantitative analogies here, more qualitative analogies. In the case of condensed matter physics, you also have quantitative similarity.
Right. Yeah.
So in a way, I agree with you. So it seems a little bit unfair to expect that type of universality in the case of Hawking radiation. But I think that what renormalization group methods do, more qualitatively speaking, is more or less what we would need in order to justify the things that we want to justify in the case of black holes. So even if the degree of universality will not be as high as in the case, or it shouldn't be as high as in the case of condensed matter physics, the type of arguments that are used to explain the universality in the condensed matter case do exactly what we want to achieve in the case of black holes. For example, to justify the use of analog experiments, you need to prove in a way that the very same behavior, even if not quantitatively, at least qualitatively, the very same behavior is present in the two systems, because only in that way we will trust on the results that we obtain in the analog case, and we will assume that these results extrapolate to the case of the target system. And the same for solving the Trans-Planckian problem, for example. This is one of the problems that appears in black hole thermodynamics. You need to show some robustness that is almost as strong as the type of robustness that you prove in the case of condensed matter physics when you use renormalization group methods. So when you use renormalization group methods, you say, well, the behavior at the critical point is absolutely insensitive towards or upon microscopic physics. And this is the type of robustness that you need to prove if you want to show that the semi-classical framework is sufficiently autonomous and it doesn't depend on quantum gravity effects. You need to show that Hawking radiation is completely insensitive with respect to possible quantum gravity perturbations, because otherwise you would need another theory that is not semi-classical theory. You would need quantum gravity to understand all of this. So in order to be to rely on the Hawking radiation in the semi-classical framework, you need to show that the robustness is almost as strong as the robustness that you can prove from renormalization group methods. So we don't expect that the degree of universality, especially universality, is the same as in the case of condensed matter physics, but we need arguments at least that can prove in a way that the behavior is both robust and universal to a high degree, even if it's not as high as in the case of condensed matter systems.
Right, but then you would compare it more to like, to the renormalization group flow and to effective theories, and not necessarily to fixed points, because
yes,
especially in fixed points, you have such a high degree of universality, and
I agree.
Also on a quantitative level, as you said.
Yes.
Whereas that's maybe not the class of universality that you want to compare.
So that's why we didn't. So I mentioned the fixed point because I was trying to sketch renormalization group methods. But if you think about our framework is based on 6 qualities, and none of these qualities depend on the existence of fixed points.
Yeah, I noticed that. Yeah, okay.
So if you have a fixed point, if you have something like exactly like renormalization group methods, and if you can derive everything from a fixed point, then you have perfect integration, the highest degree of universality that you might have. But if you have arguments that prove robustness and universality to a high degree, not as high as critical phenomena, you might have all what you need in the case of black holes, for example, without fixed points necessarily. That's why we are not comparing that with respect to fixed point or topology of fixed points, but we are comparing with respect to very general qualities that we find in the renormalization group framework.
Yeah, so if I may, a related point to this Wilsonian renormalization in gravity is that there exist arguments against this approach, namely that there's a UV-IR connection in gravity, which is also exhibited in ADS-CFT, but I mean, roughly that the Newton's constant knows about the microscopic degrees of freedom through, let's say, the Bekenstein-Hawking formula. So do you have any thoughts on this, or whether this could destroy robustness of Hawking radiation? Or
that might destroy robustness of Hawking radiation, but I tend to be a little bit more optimistic, because since there are some arguments that test some robustness of Hawking radiation, I'm optimistic that you might be able to build a framework that combines these different types of arguments in order to test some kind of robustness and universality.
Right, okay, thanks a lot.
Thank you.
Okay, the next question is from Kirill.
So I would like to better understand how the Trans-Planckian problem actually arises. I think this is the main burden to accepting the analog systems, as I understand. And so let's imagine we have a distant observer and measuring Hawking radiation coming from a distant black hole. And so then the distant observer measures it for a while and then obtains, say, it's just photons, so the observer obtains a Planck spectrum. And then as you want to go back to the source and calculate the frequencies of these spectrum, which are at the very horizon, then we get the entire spectrum blue shifted essentially to infinite frequencies. And so, first of all, is this the right account? And if this is so, wouldn't you say that the Trans-Planckian problem is actually an artificial problem which arises due to idealizations, right? Either on the part that the distant observer is actually at infinity, which is not actually the case, say any black hole source that one might think of, it is far away maybe, but not exactly at infinity. And the other case being that the radiation originating at the horizon actually is not at the very horizon, but some distance off. So are these two sort of boundary conditions, so to say, not curing this issue and impede the Trans-Planckian problem from arising at all?
Excellent. I like your way of thinking. It might, but it's hard to distinguish, I guess, what is an idealistic. Well, everything looks a little bit idealized in black hole physics, in my opinion. So that seemed to be, maybe it's a possible way of replying to the Trans-Planckian problem, and then you will have also trouble with making sense of Hawking radiation in itself, if you try to get rid of all the idealizations involved here. So it seems that Hawking radiation in itself depends on many idealizations. And one of the conditions for the robustness, for example, upon the physics of the collapse, is this exponential redshift for this at the distant future. And the converse of that is that if you have this redshift at distant future, that means that these modes were created by high energy frequencies, which is the Trans-Planckian problem. So you might try to solve that by relying on that condition and rely on that robustness upon the physics of the collapse, but I fear that you might end up destroying the entire derivation of Hawking radiation by doing that. So I'm not so sure whether that would be a way of replying, but of course it's a possibility. We might think that the redshift and therefore the Trans-Planckian problem is just a consequence of a flaw or an idealization in the argument. But if we take the argument seriously, let's say, and if we believe that the prediction of Hawking radiation is good, and if we believe that the robustness of Hawking radiation upon the physics of the collapse requires the redshift, then we have to take the Trans-Planckian problem seriously. So I think I would prefer to go in the way that we go, which is try to show that even if there is some Trans-Planckian problem, or even if the modes were created by high energy physics, we can solve that problem just by showing that not so much depends in the end on changes or variation at the high energy scales in quantum, a possibility of quantum gravity effects. So that seems to be a better way to go, in my opinion. But I admit that that might be also a possibility of thinking about this. Like also we can question the entire derivation of Hawking. I don't know if you, Eric, have more thoughts on this.
Yeah, I see the point. Just that you mentioned that indeed there is an explanation, exponentiation. So does that mean that actually the Trans-Planckian problem applies only to the tail of the thermal spectrum, which means that not the entire spectrum of the Hawking radiation is subject to the Trans-Planckian problem, but just the very tail, the very left-hand side, so to say, the very high energy of it. It's only this part which actually suffers from the Trans-Planckian problem because of the exponentiation that you need to take into account at the very source of the radiation. Is that right?
Yeah.
Okay, thanks.
Eric Curiel, your question, please.
Okay, so Patricia, thank you. That was a wonderful talk. I have a million questions, and I think most of them aren't even stupid. But before I ask you one, I'll just ask one and then throw myself at the end of the queue again so other people can ask questions. I want to make a comment about the exchange just had with Kirill, and also about a comment about Enzo's question. So Kirill, one way to see that what you're saying probably can't be right is by what Bob Garoch used to call the sociological argument. That if the problem were that easy to solve, we already would have heard about it. So it's very unlikely that such a simple answer to the problem wouldn't have been found by all the incredibly smart people thinking about it, for the past 40 years. So there's probably something wrong with the reasoning. And I think what's wrong with the reasoning is that, in fact, the redshift, as in fact, Patricia was shown by the quote that from Unruh that Patricia read early in the talk, you can actually be extremely close after collapse. 1 second after collapse, you can be a light second away from the newly formed event horizon and be experiencing very, very low energy Hawking modes. And yet, as you trace them back, they get exponentiated to arbitrarily high energies. It's not at all the case that you have to be infinitely far away and trace them back. That's just not correct. So there really is no issue of idealization here. It's important to remember in this regard that Hawking radiation isn't just thermalized at infinity, it's thermalized all throughout space-time. It's merely the case that an observer won't measure the canonical Hawking temperature, and the case that static and inertial observers won't agree on Hawking temperature except at infinity. But all throughout the interior of space-time, the static observers will see thermalized radiation at the Hawking temperature multiplied by the redshift factor. So you can be anywhere in the interior of space-time and run the Trans-Planckian problem argument. Enzo, I want to remark on the question you asked about whether or not the fact that there are so many different derivations of Hawking radiation, so many different frameworks starting from so many different places, whether that should give us some confidence that we're onto something real. The reason why I'm not very impressed by that is because, as Matt Visser in particular has just so trenchantly and clearly shown, as a mathematical fact, you need extremely little to get a Hawking effect. You need basically a Lorentz metric, and you need a one-way barrier, and you need some physical mechanism for splitting modes, and for splitting excitation modes in some physical system, and that's all you need, and you'll get a Hawking effect. So basically, these 5,000,001, to my mind, these 5,000,001 different derivations of Hawking radiation are interesting in themselves. They're clever, they're cool, they give you some different insight about different ways of thinking about things. But at the end of the day, they're all just gilding the lily. They're all just enormous number of bells and whistles that actually aren't doing any work at all. There's a very basic wheel at the center of these contraptions that's doing all the work and doing all the same work in every single derivation. So now my question. Patricia, in characterizing integration, you said that it was shared or identical mathematical properties that establishes robustness and universality. That's what's really important. But
or that the theoretical basis is mutually consistent, that they are not in tension with each other.
Well, but I'm curious how much weight you want to put on the on mathematical form there, because to my mind, what's really important isn't just that they have a shared, identical, similar mathematical form, that they're not mathematics isn't in tension with each other, but it's the physics that's the same. That there's the same that there's the same in some sense kind of causal connection between the micro and the macro dynamics that gives rise to the robustness and the integration, and that won't necessarily be encoded. So it's there. To me, there's a possible that comes apart possibly from the mathematics. It may not be the case. You might have the same or identical mathematics, but yet still have very different causal mechanisms connecting macro and micro physics. But you can also have, I think, the same kinds of causal mechanisms connecting macro and micro physics and have actually somewhat different mathematics. So it's not clear to me that focusing on the mathematics is the right way to flesh out the idea of integration.
I agree. I think in the slide, I frame it a little bit quickly because I was thinking about renormalization group methods in which you have both. So the theoretical basis, the physical basis, and the mathematical basis is the same that allows you to prove universality and robustness. But I would agree with you. I think we can leave that open as the theoretical basis, not necessarily, which doesn't necessarily mean the mathematical basis. That can be also reflect the physics behind and the causal mechanisms behind. So I would frame it like the idea that the theoretical basis for robustness and universality are mutually consistent. Okay, and I would also think more about the physical basis than the mathematical basis.
Okay, yeah, that makes sense to me. Thank you.
And that's particularly important because I think you can also think about integration arguments in other sciences like in biology, biochemistry. In which you also need in some cases analog experiments, and therefore you also need to test some robustness and universality, and you will not necessarily focus on the equations there.
There may not even be any equations.
There may not be, but that doesn't mean that you cannot have tests for robustness. Yeah. And the test for robustness need to be consistent with the test for universality. You can do genetic analysis, for example, in order to test whether the maturation of fruits is the same. And I think that's. So I want the idea of integration to be also applicable to those systems. So I would definitely agree with you. So I think instead of mathematical basis, I would replace for theoretical basis, which can be physical basis combined with mathematical basis or biological basis.
I think that last thing you said about the other sciences, I think that's a really lovely point. I really like that. Thank you.
That's something that I would definitely like to explore in a project. I think.
I'll throw myself at the end of the queue for more questions.
We have a last question from Pavan. Sorry.
Hi. So my question is about this tension you were mentioning in robustness and universality. So the question is that why are they in tension in all the three mechanisms you mentioned? Is there something characteristic to Hawking radiation that is causing tension in these two, robustness and universality?
Can you repeat that?
So you mentioned three different types of universality in Hawking radiation, and all three of them seem to have robustness and universality in tension. Is there something characteristic of Hawking radiation that is causing tension?
I don't know. That's a good question. I'm not so sure. I think not, and that's what I would like to think. So, because I believe that it might be possible to find integrated arguments in the Hawking case too. So I don't think that's a problem, or this is just based on beliefs. So I don't believe that that's a problem of the case of Hawking radiation. I think that that's a problem of the type of arguments that have been used and of the fact that they haven't been combined. So I think you might be able to combine these arguments in order to have certain degree maybe of universality and certain degree of robustness.
Okay, thank you.
Okay, I think that we are in time, and I thank again Professor Palacios for your lecture and answers. I invite who have other questions to post them on Slack, and we'll meet again at 2:30 for a student presentation. And enjoy your meal, and don't eat too much because we have to be awake. Okay, see you later.
Thank you very much. Thank you,
you.
Patricia.